where we left off on Monday. There we go. Get rid of me. Nobody wants to see that. So we left off last class. I was showing you how we do confidence intervals for the sample portion in Excel. So just kind of a remind ourselves of what we've had. So we're building confidence intervals for both sample means and sample portions, right? So, excuse me, sometimes what we'll think about, another term for these would be point estimates. So point estimate, like sometimes in the homework or good read through the book, is really just referring to the sample statistic that you're looking at. So sometimes, you know, we look at sample means or sample proportions. We then use that standard normal distribution because we knew that those sample means and sample proportions are normally distributed. So we convert those into a standard normal distribution. We can use that Z table to find how many standard deviations out we need to go from these sample statistics, and then construct a confidence interval as a lower and upper bound to be able to say that with a certain level of confidence, the true population, either mean or proportion, is somewhere in that range. Well, if I want to go a certain number of standard deviations away, then I have to multiply by what the actual standard deviation is. So that's how we were constructing confidence intervals for both sample means and sample proportions. Kind of recall, we also have equations for what those standard deviations are. We saw how we do those in Excel. So really in Excel, I mean, the main part of it was we were just using that norm.s.inv to find what that z-score was that gave us alpha over 2 on either side of our interval. Right? So I think we only worked through like 1 or 2 examples here, or I think just this example for proportions. I've got a bunch of other examples. I think I'm going to save that for Friday. So I think what we're going to try to do Friday is just look at more examples of all 3 types of confidence intervals we can build. So we've already talked about 2 of them. Today we'll talk about the 3rd, right? And then Friday we'll just kind of work through some problems. So Friday will be a lot of me presenting you guys with problems. Probably can using those eye clickers to kind of see where you're at with working through these, and hopefully getting a better understanding of how we identify what type of confidence interval we have. Okay, so sometimes I go through this a little bit different. I think I'm going to try a slightly different approach, which is present you with a very brief kind of overlook of all 3 types, and then come back together and work through all 3 of them and be able to identify when we need to apply slightly different techniques, whether or not it's a proportion or a sample mean. And then what we'll talk about today, which is if we have a sample mean, but we don't know what the population variance is. So I mentioned this already, which is that we kind of have this weird scenario where, oh, what is happening? Hold on. Why did that just happen? I think it's hold on. All right, we'll try this again. So I had this weird scenario where we don't know the population mean, but we did somehow have the population variance. That doesn't make a lot of sense, right? But we have to walk before we could run, so we wanted to work through some of those examples so that we can go to the next level, right? Which is what happens if we don't know the population variance, right? It's not going to look that much different, right? So all we're going to do is approximate that population variance using our sample variance. Similar to kind of how we're just using that sample proportion, so the true population proportion, to estimate kind of what that variance was in the true population proportion. So we're still going to build our confidence interval around our sample mean. We'll use a slightly different notation for the standard deviation of our sample means, because this is going to kind of indicate that we are still calculating that standard deviation of our sample means in a very similar manner as we were before. It's just now we're using our sample variance as the best estimate for what that population variance is. Okay? So that's nothing too crazy. But then what ends up happening is instead of being able to use that standard normal distribution, because we're using that sample variance, we're going to have to end up using something called a student t distribution. Okay? So it's the same idea. It's kind of reflecting to us how many standard deviations away we need to go to build this confidence interval. It's just at this value, and it's still going to give us alpha over 2 on either side. It's just going to be coming from a different distribution. So just like we have a uniform distribution or a binomial, normal, we're going to have something that's a little bit different here. We're going to have to use a student t distribution. We'll be talking about that today. Okay? So the student t distribution, really, I should be always kind of making this plural. Okay? So there's going to be a whole family of these distributions, right? So it's not just one student t distribution, it's really theoretically an infinite number. And so every single sample size will have its own student t distribution. So if I have sample size of 30, that's going to be a slightly different distribution if the sample size was 50. So the reason why is because we think about when I've got that sample variance, really the way that I'm calculating this we had this equation, this is going back to like exam 1 stuff. And instead of dividing by n, we were dividing by n minus 1. So if you want to think about it this way, I think this kind of helps. It's not theoretically like technically correct, but it's the easiest way to think or understand why there's different distributions. So if I had a sample that was the entire population and I just didn't realize it, which is that's a weird thing, but let's just assume that's what happens. When I calculate my sample variance, even if I had the population data without realizing it, it's still going to be a little off from what the true population variance is, because if it was population data, I should be dividing by n instead of n minus 1. So this dividing by n minus 1 is always going to cause our sample variance to be slightly higher than what the actual population variance is. Right? If I had this theoretical data set where I was treating it like a sample, even though it was the population data. So because we're dividing by n minus 1, it's always going to inflate that sample variance a little bit. So when our sample variance is higher, right, what's going to happen to that standard deviation of my sample means? Well, if my sample variance is a little bit higher because I'm dividing by n minus 1 instead of n, I'm dividing by a smaller number, this is always going to be a little bit too high. So if it's always going to be a little bit too high, you can think about this. Right? This is kind of what that pre-class video was about, which hopefully you guys kind of watched before class today and walk through a little bit more in detail. Then you can kind of go back and watch that because it's a really good kind of way to understand the student distribution. So let's assume this was our kind of like our standard normal distribution. Right? If because we're using the sample variance to approximate what the true population variance is, we said the sample variance will always be a little bit higher. So we divide by n minus 1. So if it's a little bit higher, that means the distribution is a little bit more spread out. Or what we've said in the past is that kind of flattens that distribution, right? It makes it so that values further from that true mean are more likely for us to see, and values kind of near that mean are less likely. So the problem comes up that if I'm using, say, I don't know, using the right color here. If we were to look up the z value, it gave me 0.025 in that left tail. I believe that value is 1.96, negative 1.96. The problem is, if I were to keep using that same value, but from an example where I only have the sample variance and should be using the student t distribution, notice if I'm using negative 1.96 with a student t distribution, that area is going to be a little bit larger than 0.025. So in order to get 0.025 in that tail with the student t distribution, I'm actually going to need, I don't know what the actual value is, but I'm going to end up needing a student t-value that's a little bit kind of larger, right? Here they're negative, so I'm not going to kind of say greater than, right? Because it's actually a less than, but a larger negative value. So every single time I have a different sample size, this student t distribution gets wider and wider, right? Think about kind of the reason why. If I had a sample size of 2, well, dividing by n minus 1 there, so 2 minus 1 is 1, dividing by 1 instead of 2 will greatly influence how far off that sample variance is going to be. If I divide by 999 instead of 1,000, that doesn't have near as much of an effect, right? So every single sample size, how far off our student t distribution is from the standard normal will depend on what that sample size is. Okay? So we've got this family of distributions, but they're very, very similar to a standard normal. Okay? They're still symmetric, right? They're a little bit more spread out. And how we identify which one of these student t distributions we need to use, we'll start calling it this term of degrees of freedom. Right? So we'll kind of go a little more in depth into this when we get to a topic called regression in this class. But for now, let's just kind of learn the rule, right? I think it'll make a little more sense when we're kind of addressing it in different topics. But the idea here is, because we're dividing by n minus 1, this degrees of freedom kind of tells us how far off we're going to be by just using the sample variance instead of the population variance. So we identify what student t distribution we need to use using this degrees of freedom, which is simply just the sample size minus 1. So it's still symmetric. I kind of mentioned this. So that was a property that the normal distribution had, or sorry, not normal, standard normal distribution. The student t distribution is normal. It's just not standard. It's not standard normal distribution. So it's still going to have a mean of 0, but the variance is going to be a little bit greater than 1, right? The variance is going to be a little bit higher, right? So it varies from that standard normal distribution a little bit. Excuse me. As that sample size gets higher and higher, that student t distribution, right? I said as the sample variance gets higher and higher, we get, dividing by n minus 1 doesn't matter as much. So the higher the sample size gets, the closer and closer the student t distribution gets to that standard normal, or the closer and closer the variance on that student t distribution gets to 1. Right? We're kind of approaching that standard normal distribution. So I said like 100 here. I'll end up showing you a table where, probably to be safe, we would want to think about really anything over 1,000. We can't even distinguish a difference between the two. At a sample size of 100, we can use the standard normal to approximate a student t because they are so close, but you can still see the differences. Once you get to a sample size of 1,000, you can't even see the differences out to like the 5th decimal point. So I kind of already, I have a drawing here, which is kind of like one I did before. So we keep using those old z values. You kind of notice here, yeah, that would give me 0.025 underneath that black curve or that standard normal distribution, but the areas underneath the green and the blue curve are going to be much larger. Right? So actually, I think you can calculate those are quite a bit larger than 0.025. So in order to build our confidence interval, we still need alpha over 2 on each side. We'd have to use a much higher t-value to do that. So the table, I'm not even going to waste time here. I'm just going to show you the table that I put up on Canvas, because that one's probably, and my computer's having all kinds of problems this morning. So let's go here. Oh, I think I just left it in here. Oh, there it was. Hopefully rotating. There we go. So it's going to work a little bit different than the standard normal table. So with a student t table, the actual t values are in the middle, right? So with the standard normal, the z values were kind of the row and column headings, and then the probabilities are in the middle of the table. With the student t table, we're going to have the actual t values in the middle, and then our probability or area in the tail is going to be what's on our column headings. So the way that we would read this is if we wanted, and unlike the standard normal, the student t always looks at the right side of the distribution. Now it's symmetric, so if I wanted to look at the left side, it would basically just be all these numbers. They would all just be negative. Right? So if I wanted to say 0.05, actually I think the value of even is 0.025, right? So let's use that. I wanted 0.025 as the area in that tail, the t-value that would give that to me, I had degrees of freedom of, say, 6. The t-value that would give that area in the tail to me would be 2.4, which varies, right, from 1.96. Now, what t-value I need to use to get that area in the tail is going to depend on what my sample size is. So notice that when my sample size is relatively low, which would kind of reflect, be reflected with low degrees of freedom, these values are like 2.5, 2.4, 2.7, quite a bit off of 1.96. But as my sample size and my degrees of freedoms get higher and higher, keep scrolling down here, notice the t-value that I need to use starts to get smaller and smaller and starts to approach that value of 1.96. Okay. Once I get to a sample size of 1,000, notice I'm only off of the third decimal point here. Right? I mean, 1.962. Right? So I'm getting really, really close to what that value I was using from the standard normal distribution was, because my sample size is getting larger and larger. So the value of my n-1 doesn't matter. But for those relatively low sample sizes, I need to use a t-value that was quite a bit different than the value I was using for a standard normal. Right? 2.4, 2.7. Now, so that's kind of how we read this table, right? I find the area that I want in my tail and my degrees of freedom based off my sample size, and I kind of find where those two meet. This table will tell me that t-value that at that degrees of freedom gives me that desired area in the tail. Any questions before I kind of keep going here? Is this making some sense? A little bit? Okay. So one thing I want to point out here, since we're looking at it, is as the sample size gets higher and higher, we're really just approaching, or our student t-distributions are starting to look more and more like the standard normal. So if we could theoretically have an infinite sample size, which in practice, right, that doesn't even make any sense. How can we have an infinite sample size? But if we were able to get up to an infinite sample size, what should be true is that student t-distribution would actually be a standard normal, right? If we're just approaching, getting closer and closer to that standard normal, if we continue off to infinity, once we kind of look at that infinite sample size, we would actually be right back at the values that we would find from the standard normal distribution. So notice this very last row of the student t table, it's actually telling you there's a standard normal value you would need to have alpha, whatever that desired area in the tail is. So kind of a nice cheat, and also this table goes out to 3 decimals, is that instead of using that standard normal distribution every time when we're doing these confidence intervals to find what value you need, you could actually just use this last row of the student t table, right? It's kind of like, here's the student t tables, and here's this one last comparison group on the very last row, which is your standard normal. So if it makes more sense, just think of this last row on the student t table is actually just like an added part to it, which is here's the standard normal values that you would find if you wanted to get these same desired areas. So we can be a little more precise. So notice, like, I think we want a 0.1 in the tail. If we go back up to the column heading, I think this column is 0.1. When we use that standard normal table, we had to like, oh, okay, I'm in between these two probabilities. I think you can get pretty close. I'm in between 1.28 and 1.29. Well, here, I'm in between 1.28 and 1.29, but this table tells me out to the third decimal what the actual value is. So I'll kind of start as we work through some problems on Friday. I'll probably exploit that a lot instead of like pulling up the standard normal table and punting for the probabilities. I'll just pull up the student t and look at the very last row. Any questions on that? Sometimes that can be a little confusing. It's like, kind of like we have 2 tables almost in one here, in the sense, but I say 2 tables, the second table is just 1 row, but it does kind of make it nice. We've got both the student t-distribution values for building confidence intervals, and that very last row will give us the standard normal distribution values for building confidence intervals. So I already have this up on the board. Oh. But really, once we plug our values into this confidence interval equation, yeah, this is coming from a different distribution, this t-value, But once I plug the number in, really, it looks exactly the same, right? Unless I'm looking at the notation, it won't look any different when I have the actual numbers plugged in. So, just like before, we basically have the exact same steps. Identify what the problem gives you. So your sample mean, sample size. I said the problem gives you. In practice, you can actually take the data, calculate the sample mean, calculate your sample size, calculate your sample variance, and then whatever level of confidence you want, that gives you your desired alpha, right? And all the properties of kind of how alpha lines up with confidence intervals or confidence levels is the same as the previous confidence interval examples that we were looking at, right? So 95% confidence is still an alpha of 0.05. That doesn't change at all. We then look up, instead of a z value, now it gives us alpha over 2 on each side of the confidence interval. We look up a t value, it gives us alpha over 2 on each side of the confidence interval. We can do step 3, which is like calculate, use that intermediate step where we calculate the standard deviation of our sample variance or our sample means, or we can just do it all at once, right? So step 3 is kind of optional, right? It can like built in just to our confidence interval equation. Then we add our margin of error to our upper bound and subtract our margin of error to our lower bound. And that's kind of the same as what we were doing before as well. So not a lot has changed in terms of the procedure of how we'll approach these problems. The main thing that's changed is we're just using a different distribution, excuse me, because we only have a sample variance now instead of this known population variance. Let's take a drink real quick. So let's work through a problem here. This one's not overly interesting. I could have sworn I'd follow water. Doesn't have a lot of context, but it gives us some values that we can start working through to build an actual confidence. So here I've got what? I have 36 observations in my sample. I find a sample variance and a sample mean of 9 and 324. Okay. So what I've essentially got is everything that I need to plug into that equation. I've got my sample mean, my sample variance, and my sample size. The only thing left that I need is that t value that gives me the desired alpha over 2 on each side of my confidence. So I need one more thing, which is what level of confidence do I want to build this interval for? So if I have an alpha of 0.01, I would be building what level of a confidence interval here? What would my confidence level be with an alpha of 0.01? Yeah, 99. I'm okay with awkward signs. So 99%. Remember, alpha is just set outside my interval, but in decimal form. So if alpha is 0.01, really what I'm looking for is what would the t value be? The kind of t values, one negative, one positive. That gives me total of alpha in those tails, or alpha over 2 in each tail, or 0.01 over 2. So 0.005. Okay. So I have to go to my student t table. Now I need one more piece of information, because when I'm dealing with student t distributions, I need to know which student t distribution am I using. Okay. Now I said the degrees of freedom is simply going to be n minus 1. So here, 36 minus 1, we'll have a degrees of freedom of 35. So I go to that student t table, and kind of for future classes, it would probably be beneficial, just like with a standard normal, to kind of print that out if you want to have that in front of you. You can pull it up on your laptop or your phone or whatever, but if you want a physical copy kind of to look at right in front of you, that might be helpful. So I'm going to go up here. The alpha divided by 2 value I was looking at was 0.005, so I'm going to be using this column. The degrees of freedom that I had was 35. So go over that t value that I need to be using to get that desired alpha over 2 in the tail be positive and negative 2.724. Now that positive and negative is already built in my confidence interval kind of equations there, right? So once I find the values, I don't really have to think about the fact that there are two, because I'm using that same value, but adding it to get the upper bound, subtracting it to the lower bound. Now it's just a matter of plugging everything in. So I believe the sample mean that we had was what, 9? Equal sign, plus and minus. All right, so I'm just going to start plugging things into that confidence interval equation I have on the other side of the board. So the sample mean was 9. The next thing I needed was that t-value. Well, we just looked that up. That was 2.724. And I can calculate, you can do that intermediate calculation if I wanted to, so that I'm plugging in that standard deviation of my sample means, which was just the square root of my sample variance, which I believe the problem told us was 324, divided by my sample size, which was 36. Yeah, want to help me out with this one? This would be what? 9? No, this would be 3, I think. That calculation is wrong. Speak up and let me know, but I think I'm looking at this correct in my head. It should be a sample, should be a standard deviation of my sample means of 3, right? And I can just plug that in, and now I'm done, right? I add that margin of error to my upper bound, I subtract it to my lower bound, and then I can say with 99% confidence, the true population mean is somewhere within this range, right? So if we, I think I've got all of that here. Now, notice sometimes we have examples. Here we've got a relatively large sample variance. We have not the largest sample size, and so notice our confidence interval is very wide here. I haven't been able to pinpoint down where the true population is at all. In fact, this doesn't have this example doesn't have any kind of context to it. So in this confidence interval almost includes the value of 0. So probably not be able to make a whole lot of statements with this. But now we'll kind of look at one that has a little more context next. Yeah. Oh, yeah. So this is one we can start to think about the confidence interval in slightly different ways. I think I mentioned this last class. So we're always kind of adding and subtracting what we call the margin of error. So I just kind of did this calculation, 3 times 2.724. That's how I got 8.16. So that 8.16 would reflect my margin of error. It's not as useful when we're looking at sample mean examples. When we're dealing with sample proportions, usually that margin of error has a slightly clearer interpretation, which is like in political polling and stuff. Anytime they tell candidate X, we found in this recent survey, is predicted to get 48% of the vote with a margin of error or plus minus 3.4, 3.4. What they're really telling you is that margin of error that you could use to then build your confidence interval to get your lower and upper bound. So we can always calculate that. It's usually not, its real value is to be able to construct a lower and upper bound. So we don't have to calculate that if we don't want to. I just kind of did it here to show that you can kind of do this step by step. It also just makes it so that, if you break this up into as many parts as possible, it's always like easier to prevent from making mistakes in your calculator. That's also another. Any other questions before we keep moving forward here? All right, pretty good. So we're through one more example, and then I'll show you how we do this in Excel. Okay? It really is going to not be much different than what we did on Monday, but so hopefully I can rewrite that here in a second. So let's say that the American Medical Association says that the average starting salary for physicians is $175,000. So maybe this is like a cynical, this probably speaks a lot about who I am as a person, But I think the real value of confidence intervals is anytime someone tells you something, you can always kind of check it with data, right? So if someone comes up to me and says, yeah, the average physician makes 175,000. I started looking at the data. I'm like, yeah, it sure doesn't look like it. So I can use a confidence interval to be able to tell them if that value is wrong or not, right? So I look at that value. I'm like, I don't think that's true. I go out, I look at a sample of 81 physicians' salaries, and I find the sample mean of 160,000. So just to kind of recall what we're doing here, building this confidence interval. We're going to need 4 different things. So the first thing is this sample mean. So I take this sample, and I find a sample mean of 160,000. I find a sample variance of 324 million. And that was from my sample that was of size 81, right? 81 physicians. So if I have the equation in front of me, which like on the exam will, which I'll mention something about the exam right before we do class today. So don't let me forget that if I don't say something. All I've done here is plug the values, right? And the notation I can even line up, and given you'll have the notation, just figure out where those values plug in at. The real tough part, or the part that takes a little more work, is looking up that t-value, right? So here, if I wanted to build a confidence interval with an alpha of 0.05, I'd be building what level of confidence? Alpha of 0.05 corresponds to what percent confidence? 95%. So, building a 95% confidence interval, an alpha over 2 here, or the area that I want on each side of my confidence interval would be 0.025. The other thing that I need is my degrees of freedom, which here, 81 minus 1, so I've got degrees of freedom of 80. Okay. So I'm going to go to that student T table. Pull that up. We wanted 0.025 on each side. Now I need to find my degrees of freedom over here on the left-hand side. So I start scrolling down. Here's my degrees of freedom of 80. The t-value I need to get that 0.025 on each side of my confidence interval is 1.99. Right? So now I get the last piece of information that I need. We'll look at upper and lower boundaries. Right? Any questions or anything you step there, or what's this change? Yeah.
So where do you use the 80 bucks? Is that just for the
So remember when we went to that student T table?
Oh, never mind, yeah.
That was my degrees of freedom. Like in the equation, you don't really use it. Yeah, it's not, I mean, it is that 80 is allowing you to identify which one of this huge family of student T distributions they can use. Other questions? So I think if we go through, not thinking that in my head is as great as some people. So we calculate that intermediate step, right? It could have made life a little bit easier. So instead of doing this all at one time in our calculator, we could have calculated that standard deviation of my sample means ahead of time. That gives us a slightly easier value to kind of plug in. Now I've got a little bit more simple of an equation to enter in my calculator. Once I plug those values in, though, I get what, 156,000 to 164 about, rounding a little bit here. So I built this 95% confidence level. So I'm saying that with 95% confidence, based off of the sample mean that I saw, right, that the true population mean is somewhere in this range. So the population mean value could be here, could be over here, could be here, could be anywhere in this range of values. Right? But notice, what's one value that's not in that range? Oh, back too far. There you go. that 175,000 that the AMA was saying is the actual population. I could go to them and say with 95% confidence, you're lying. Right? 175,000 is not in this range of values. The true population, what I'm saying when I built this confidence interval is the true population mean is somewhere within this range of values. So if someone comes up to me and tells me that the true population mean is 175,000 without any data to support it, I can look at them and say, based off my sample, it's not. Right? Based off my sample, the true mean is somewhere in this range of values. Okay. Any questions? All right, so we're gonna have everything kind of up there on the board, but also on this slide. I think the next thing that we're gonna work through, okay, no. Okay, here I go. I've got kind of a summary of what we're gonna do in Excel here, but I'll kind of walk us through it. So we'll use that confidence interval blank file that, or Excel file that we're using last class. And we'll see how we could do or build a confidence interval when we only have a sample variance. So I've got two examples here. I can't remember which one I think is more interesting. Well, I use height all the time, so let's use something else, right? So here I've got some drug death data. So this last sheet, unknown population SD. So this is, we don't know the population standard deviation. Now it's all filled in here. I'm going to leave this here just for the sake of, we hopefully are good with this. I'll review it, but I'll kind of show you how we could build these upper and lower bounds. So I'm going to delete these, right? The complete file. I'll get posted after class today since we've kind of worked through each one of these three types of examples in class. So I've got 2012 data and 2016 data. I've almost got like two data sets here, right? Just two different time periods. I've got a bunch of different counties and what their drug deaths per 10,000 people in that county were, right? So, I don't want to just look at the drug deaths because I'm guessing Adair, right? Adair County is much smaller than Boone County here. Right? So we'll use that kind of death rate. Right? Might make it a little bit easier. So instead of, so I've got here just looking at the average or the mean of those drug deaths. Sample size, we found that using the count function. And now my sample variance, right, just goes back to using that var.s function. Right? So the other example that I worked through on Monday, I was giving you a population variance. In practice, what's more realistic is I have some data set and all I can do is calculate the sample variance from that data, okay? Well, these were three of the things that I needed for my confidence interval. The only other thing I need was what t-value gives me the desired alpha over 2 on each side of my confidence interval. So Monday, what we said, if we have a proportion example or a sample mean when I know the population variance, does anyone remember what function we were using in Excel there? So if I knew the area I wanted in the tail and I wanted this function in Excel to give me the z value, I used what function? I don't remember. Thank you. Yeah. So norm.s.inv. Right? We were working in reverse because we knew the area we wanted in the tail and we want Excel to tell us that z value. Well, now we're doing the same thing. We know the area that we want in the tail on each side of our confidence interval, but we need Excel to tell us the t value. So we're still kind of using this inverse process, but we're using a student t distribution. So instead of norm.s.inv, it's just t.inv. Same sort of idea. Okay. So we use this t.inv. Now it has, instead of just one thing that we have to tell Excel, we've got two things. Okay? So the first thing is, what's the probability that we want on each side of the confidence interval? Well, that's just alpha divided by 2. But the second thing we now have to tell Excel, because we're looking at the student t distributions, is, okay, which distribution should I be using? Which student t distribution should I be using? And that's based off my degrees of freedom. So I tell it, well, here's my sample size, -1, right? Now, if I was programming this, I don't know why they don't just have you put the sample size in and then calculate the degrees of freedom for you, but that's how it is, right? That's how this function works, right? So we tell it the area we want in the tail, just like we did before, but we also have to tell it the second thing, which is our degrees of freedom, or sample size -1. Now, one thing we talked about on Monday as well is if I just hit enter here, I'm always going to get that negative value. So the student or t.inv function works just like the norm.s.inv function in Excel, which is that whatever probability you tell it, it's treating it as though that's the left side of the distribution. Okay. Well, we just want the value. So we said one of the things that we could just do here was take the absolute value. And now we just get the same t-value, but positive. Right? Now, if I try to copy this down, I have a problem. Right? Oh, yeah. It's updating that cell reference where my sample size was. Okay. So we'll go back in. F4, Command T on a Mac, freeze that cell reference. Now, when I copy this down, I can get my t-values for these 3 different levels of confidence. Okay. Now, notice these vary from what we're using with a standard normal. So 1.65, 1.98, 2.61, a little bit higher than those values for those examples we did on Monday that came from a standard normal distribution. Okay. From here, everything's exactly the same as what we did on Monday with sample mean examples. We'll build our lower bound by taking the sample mean, subtracting our margin of error, which is calculated by taking that t-value, multiplying it by the square root. Oh, that is not right. The square root of my sample variance divided by my sample size. So I think on Monday, I kind of showed you some examples where we calculated that standard deviation of our sample means ahead of time. You can do that in these types of examples as well, but you can also do it all in one line, right? Or all within one cell. So I just wanted to kind of show you both ways. Right? So when I want to copy this down to build the confidence interval for 3 different levels, I'm going to want that t-value to update, but nothing else changes. I should be using the same sample mean, sample size, and sample variance. So everything but that t-value, I'm going to freeze those cell references. Okay. Now when I copy this down, everything here stays the same, but it keeps updating that t-value because if I want to do different levels of confidence, I need to be going out a different number of standard deviations, right? I need to go out a higher number of standard deviations to build a higher level of confidence. Kind of reflected, right? Higher levels of confidence correspond to lower alpha values. So you see here, I'm kind of using larger t-values down here. Any questions over anything? Yeah. Oh, so, right, when we're building different levels of confidence, my alpha is always going to be different, right? But my sample size should never change. So that second thing that we told it, we should be freezing that sample size cell reference. Or, we could just type it in, but if we're copying it, we'd have to kind of use that, or we'd have to freeze that. Any other questions? Or keep moving here. Okay, so the only thing left to do is find that upper bound. That's where we said double click on that lower bound cell, copy, hit enter to get out of the cell, paste it, and instead of subtracting my margin of error, I'm going to add my margin of error. That's the only thing that we have to change. Copy that down, and now I've got 3 different confidence intervals, right, relatively quickly. Okay. So the only difference from what we did Monday, this is why I said if you try to kind of tackle that Excel assignment and do problem 3, you probably if you just treated if you found the sample variance and treat it as the population variance, you probably have every single thing right, except for instead of using z values, you should have been using t values. But even if you did that work, just go in, change your norm.s.inv functions to those t.inv functions, and the actual construction of your lower and upper bound would be exactly the same. What did and I could do this for 2016 as well. Actually, I'll do this relatively quickly because I want to just show you all of it again. But I do want to make a point. So I'll freeze this. Oops. I can flub these keys. So just to kind of have something here, I'll copy this, paste it, add my margin of error to get my upper bound instead of subtracting it to get my lower bound. And if I'm looking at this and say, you know, someone says, have drug deaths increased over this time frame? Well, if I look at these confidence intervals, I mean, they're almost entirely overlapping each other, right? So we said anytime we have confidence intervals that overlap, we can't really say whether or not one group is higher than the other or lower than the other. So here, we really can't say based off of the sample evidence that drug deaths have really changed at all of these time periods. Now, if we just look at the sample mean, right, I believe the sample mean looks like that they have, right, goes from 2.45 to 2.5 deaths per 10,000 people. But that's just the sample mean, right? We have to build our confidence interval around that. It could be that we just happen to get a sample mean from, you know, kind of far away from where those two populations are. So this should be kind of enough to kind of tackle the rest of that Excel assignment. Like I said, when I'm done teaching my classes today, I'll kind of change that due date to be the other day on Monday. So for the exam, kind of looking at things and trying to predict what we'll be able to get through next week. I think tentatively the syllabus had our exam date is next Friday. I'm going to push it forward to kind of that next week and tentatively, and 99% confidence. I can tell you, I think we're going to do it on that following Wednesday. So that would be what, the 10th. Okay. So we have a little bit more time. We've got one more thing we need to cover before we take that exam, which will be hypothesis testing. So we'll start that on Friday. Okay. Other than that, there's no questions for me. Get out of here. Okay. All right, so I will see you guys on Friday. I'll put an announcement up about the exam date change as well.